Hi everybody, my name is Alex Bradbury. I'm the CTO and co-founder of lowRISC. Today I'm going to be talking about our work on the RISC-V LLVM backend. I initiated a few years back now the upstream RISC-V LLVM effort, and I'm upstream code owner. At lowRISC, since then, we've grown our compiler toolchain team. We've reached major milestones in terms of the upstream RISC-V LLVM support, and I'll be talking about exactly where we're at today. Right, so just a few words about lowRISC. We're a not-for-profit company based in Cambridge, UK. We have a full-stack engineering team. We tend to work on projects collaboratively with our partners, LLVM being one example of this, working with a number of other companies within the LLVM community, but we also span hardware as well. I'll mention a little bit at the end. You may please come and talk to us at our booth to find out more about the OpenTitan hardware silicon root of trust. So in this talk, I'm going to start with saying just a few words about LLVM and Clang for those of you who haven't been exposed to it before. I'll say a little bit about the implementation approach I've taken, though sticking to a fairly high level. If you want more technical details, then go and look up my talk from the LLVM dev meeting about a month ago now. I'll detail the current status and the major milestones we've reached, talk through how we got there in terms of what we found worked and lessons I think that other members of the community could learn for other software projects, as well as, of course, challenges and future work. Now, first, a very high-level introduction to the LLVM compiler toolchain. For those of you who aren't familiar, it is a suite of compilation tools released under a permissive open source license, so a derivative of Apache. It is commonly paired with the Clang C and C++ language front end. It has seen extensive commercial and research uptake with companies like Apple, Google, Facebook, ARM, all investing significant engineering resources in it. You might wonder why there's interest in LLVM and Clang when GCC exists and is a fantastic compiler. That's certainly true. But there are a number of reasons people are interested. Sometimes it's down to licensing, so the fact that it's under a permissive rather than copyleft license is interesting for some users. Many of us also appreciate the modern library-based C++ design, which makes it relatively easy to make new modifications or try out experimental features. It's also well known for having a well-defined intermediate representation, LLVM-IR, and a very powerful infrastructure for writing custom passes around that, so custom transformations. Just to briefly detail, so you have some idea of where the work gets done in bringing up a compiler on for a new target. I've kind of highlighted in sort of reddish pinkish color the main areas of the LLVM and Clang toolchain that we tend to touch. So the Clang front end, so that's what's handling your C and C++ input. There are a small number of changes, not all that much, mostly related to handling ABI and command line options and any other target and a few other target-specific front-end features, such as setting particular defines. For the middle end, there's not really much, really anything to be done. This is one of the advantages of a compiler infrastructure for the majority of the work, which is doing transformations on the intermediate representation is reusable and cross-target. Where most of the work gets done is in LLVM code gen and the LLVM MC layer. So the code gen step is taking your intermediate representation, so an internal LLVM representation of your program, and ultimately translating that to RISC-V instructions. The next step after that is what's labeled here mysteriously as the MC layer, which is just the machine code layer, effectively the assembler. So once you've decided that you want to omit a RISC-V add instruction, your assembler then needs to go and decide exactly how to encode that and to generate an ELF file and all of these sorts of things. As a little bit more technical background on what makes up an LLVM backend here. Again, a lot of the work is related to both specifying instruction definitions, so which bits go where in your instruction encoding, also instruction patterns, so this matching between your LLVM-IR add instruction and your RISC-V add instruction, for instance. And then there's a whole bunch of extra work in order to make use of the sort of target-independent infrastructure that LLVM provides. A lot of this is in the form of target-specific hooks, whereby the target-independent code will sort of query properties of the architecture in order to decide which code gen choices to make. Inevitably, a whole bunch of extra C++ logic to hook it all together. And in practical terms, this results in particularly as the project matures, a long tail of tweaking, bug hunting, and bug fixing. Our development approach has been, from the start, I think in the early days of RISC-V, I sort of came to RISC-V community with actually quite a lot of background in LLVM. So I ported LLVM into a research architecture before when at the University of Cambridge. I saw that there was some really interesting work on RISC-V LLVM from a UC Berkeley student. So they had an initial port available, but it was heavily derived from the MIPS backend. And although a lot of things did work in it, there wasn't a clear pathway to getting that upstream because there's a lot of cleanup. There was not a strong story in terms of unit testing. And it was, I think the issue that we saw was that particularly at that time when a lot of people were just trying, it was early days for RISC-V, so a lot of people were trying very early stage R&D projects or early experimentation. They'd take that downstream backend, they'd make a few fixes until it did what they needed to do for their kind of fairly short-term project, and then that work would be lost. There wasn't a particular upstream to push it to. So I was very keen to invest in getting high-quality upstream support, which everybody can benefit from, everybody can add to, and can be integrated into the standard LLVM release process, and ultimately grow a larger community around it. This took an incremental approach. I think us compiler developers will often complain about the variety of options that RISC-V has in terms of optional ISA extensions and different ABIs. But there is a benefit to it in terms of bringing the compiler tool chain up, because it is actually quite nice that you can start with just RV32i and RV64i and a single ABI, and then add in support for extra instruction set extensions and ABI as you go. I guess from the beginning, we were keen to take a very collaborative approach. This is both in terms of the technical approach, so putting the work that were out there, sharing it with the wider LLVM community, making use of its review process and RFC process for sharing planned implementation approaches. But for lowRISC, also in terms of the business model for supporting the work that we're doing. So I mentioned we're not for profit, but the RISC-V community were very keen to see this work take place. So we were able to attract support from some early adopters of RISC-V, contributing both funding for low-risk work as well as support from engineers who we'd worked with to help push this forward. So this is exactly the sort of engineering model that we were set up to make use of. It's been successful here with LLVM. We intend to continue using it for LLVM and Clang, and we see it again in OpenTitan. Now, in terms of RISC-V LLVM status, I'm pleased to say that, yes, it is now a default target as of the LLVM and Clang 9.0 release, which was in mid-September. Now, for those of you who aren't LLVM developers, it may not be clear what exactly that means. Effectively, prior to that, it was marked as an experimental target. You can think of this as like a kind of an incubation space for targets which are in development. So it's committed upstream, yet not enabled by default for all compiler builds. And so it's fine for people who are willing to go and build their own version. But if you go and download a pre-compiled binary, it wouldn't have the RISC-V support built in by default. And it's kind of accepted that there may be a few holes and a few issues that people haven't got around to fixing yet. And so part of moving from an experimental to a standard or default backend was demonstrating that we'd worked through all the major issues. And the benefit is that it can now be distributed to a much wider community of users. And it's much easier for people who are doing different front-end languages. So I mentioned that Clang is commonly used with LLVM, but increasingly other languages such as Rust, Julia, and Swift also motivate the use of LLVM, all of which rely on LLVM as their compiler backend. In terms of what's available and complete, we have fully functionally complete RV32 IMA-FDC and RV64 IMA-FDC support. All of the ABIs, other than the embedded ABI, which Sam on my compiler team is currently working on. Around the time we did this, we did an awful lot of test and validation work in order to justify that change from experimental to a default backend. I think the most interesting piece of that was probably around building a huge corpus of Linux packages with build root. So somewhere over 2,000 packages demonstrated working. All of the ones which failed to build, which we looked into, we could only find build system related issues as opposed to any internal compiler bug. And of course, throughout this effort, we've been making use of standard test suites and benchmarks and the like. In terms of other LLVM-related projects, the compiler RT, the kind of compiler support library, that's ported, fully functional. There's also been plenty of work in the wider community on LLD, the LLVM linker. This was started by Andes. Further work has been done on it from a range of other contributors. And just recently it was reported that it's now possible to link a full FreeBSD system, kernel and user space, with just a few minor fixes. So I saw a couple of patches turned up on my review list earlier this week, which we'll get to shortly. And the major missing feature there is linker relaxation, which is an extra performance optimization, but not a correctness issue. Just to step through a few kind of key stats, that's always fun looking at this sort of project. And these are maybe a couple of weeks out of date now from when I wrote these slides. I think we had almost 380 commits touching the sort of main subdirectory within the LLVM backend, around almost 9,000 lines of C++ in that directory. For those of you familiar with the LLVM implementation, you may know there's also a whole bunch of extra logic in a domain-specific language called TableGen, so including white space and comments around an extra 4,000 lines, which is mostly in specifying the instruction definitions and patterns for code generation. And just as a sample of the kind of testing we have in tree, we have around 160 individual test files, many of which containing dozens of tests within the for code gen, and again many more for machine code layer and in other LLVM test suites. I suppose another potentially interesting statistic there could be looking back at the amount of comments in review threads, because I think that's almost the tip of the iceberg. If you look back at some of the initial work we did and the wider LLVM community, a lot of patches would end up generating a large number of comments and back and forth and updated patches during the review process, all as a part of the work to try and get code quality and testing to the highest point possible. So in terms of how we got there, this is a rough timeline just cherry picking a few milestones. I'm not sure if the contrast may be a bit low there, apologies for that. Fairly arbitrarily, mostly limited by what I'm able to fit on this diagram nicely. The initial work on this actually started around the end of 2016. At that time, it was basically a few weekends and a few evenings experimenting with this to see if it looked feasible and trying to scope the project. Throughout 2017, work ramped up. We were able to get some support from some members of the RISC-V community, and then ramping up further still in 2018, and particularly from the end of last year and throughout this year, as we've been able to staff up our compiler toolchain team, and also the community of contributors has been growing as the backend is becoming more and more stable. And to that point, we're grateful to the huge number of contributors who have joined this effort. So this is almost certainly incomplete listing of people from a whole range of companies, including Google, Qualcomm, Embercosm, Andes Tech, and many more who've contributed in terms of code submissions, code reviews, feedback on RFC threads, and much more. I think one of the LLVM effort has been, I think, a huge success story for the LLVM community and indeed the RISC-V community, as even for LLVM, which is a hugely successful open source project, I think the level of collaboration, particularly on something at such an early stage across companies, has been quite novel. Often a compiler team at one particular company will do a large chunk of work and then share it, particularly as often work on new ISAs is embargoed, but we've been able to work very effectively with a range of companies. Part of that success has been through coordination. So we run weekly community RISC-V LLVM calls where the sort of active contributor community dial in and discuss patches which are up for review. This isn't really about sort of long-term planning or support requests. It's primarily stepping through things which are in review, highlighting work which people are about to take on, and generally making sure that we don't end up with duplicated effort. It's also a good opportunity to try and for people to surface things. For instance, if there's a discussion brewing in terms of ABI specifications, or maybe some work going on in the binutils or GCC world. We've put a continual effort into outreach in terms of spreading the word of what we're doing, trying to attract new contributors and make LLVM more accessible for people. So you might want to go and look up my LLVM tutorial and coding lab from the LLVM dev meeting last year. And as I alluded to before, a huge amount of testing is actually a nice example, I think, of where we've been able to contribute back to the wider LLVM community. For people who've attended previous talks about the RISC-V LLVM backend, you'll know I'm quite keen on using the GCC torture suite for initial backend bring up. So this is a set of around 1,600 relatively simple C tests. The advantage of them is that because they're so small and simple, when you find a bug, when it shows a bug, it's actually incredibly good news, because compared to finding a bug in some 100,000 line or 10,000 line benchmark, it's actually pretty easy to go and figure out what's going on. So we've done some work this year, Sam Elliott on my toolchain team, to clean that up and submit that test suite is now incorporated into upstream LLVM alongside all the necessary build scripts, and that's now used by other backends as well. And we're seeing this adopted by a number of companies who are often somewhat secretive about what they're doing. It's slightly odd because as we get the backend continually matures, I get less feedback from people, because a lot of people got in touch when they found that there was a feature that wasn't there yet, or they found a bug. But now when I bump into people at these conferences, it's often, oh yeah, we're using it for our internal firmware build, and there are several major players in RISC-V space who are using it for their firmware build. We've been making increasing use of Rust, which of course is using the LLVM toolchain for OpenTitan. So I have a short amount of time left, so I'll just highlight one or two challenges. I think an interesting one that we're starting to look at in the LLVM community, and I think the wider RISC-V community needs to consider, is how to handle the work in progress standard extensions. So we're seeing things like the vector spec, where there are some early patches which are circulating, the same with the bit manipulation extension. It would be, I think, better if we were able to merge those upstream, but what we don't want to do is have a support requirement for them, because we want to enable people to collaborate on the development of those extensions and have that feedback into the ISA development process. But I think we'll need to ensure that it gets put behind a suitably scary compiler flag, so that it's very clear that it isn't, it is not yet reached full support and ratification. There's also maybe some challenges we're seeing there around, I know multiple firms are starting to announce vector products which implement the vector specs. So a concern for me as a compiler developer would be people shipping products based on unratified specifications, and us having to support multiple versions of the vector spec. So hopefully we can try and avoid that as a community. So I think in the previous talk covered a reasonable amount of detailed work which is going on the vector spec. I understand that it's actually an area where it seems there have been multiple people working on it. So Robin Krupp has done a lot of work on the vector spec. You may have met him at some previous workshops. It seems there's now some parallel work going on with Sci5 and others, which hopefully can all sort of join together in a common effort. There's, as was mentioned in the previous talk, code size is of great interest to the RISC-V community. We've sort of done some of the obvious cleanups and improvements. There's work coming in from contributors like Embercosm in order to enable further code size optimization features. And again, there's more work to be done in terms of tuning. It's for people who've kind of followed similar efforts on ARM and other architectures, you'll know that there's a kind of long tail of cleanups and improvements to explore. And so I think we don't have any time for questions now, but if you have any questions about the work that I've been doing, please come and talk to us at our booth on the expo floor. You can also come and find out more about other projects we're doing, such as the IBEX RISC-V RV32 IMC core, and OpenTitan, the world's first open source silicon root of trust, which we're building in collaboration with our partners Google, G&D, Western Digital, Nuvoton, and ETH Zurich. So please come and talk to me then. Thank you very much.